So now we are going to get started with alkene reactions, which are primarily addition reactions, okay? But there will be some more as we go on. So let me introduce a few things here for you, okay? So first of all, we are doing alkenes. Alkenes are a hydrocarbon and the functional group is going to be the double bond, right? And so we already know that the smallest alkene is this one, which is ethene. I just wanted to give you an idea of how we are going to be approaching organic chemistry in my class. And what we generally do for any kind of functional group is we go through nomenclature, we learn how to name things, we learn about their physical properties, we learn about their applications or where they are obtained from, things like that, anything of general interest for us. We will learn how to synthesize those kind of functional groups, and then we will learn about reactions, okay, for all functional groups. So this is generally the trend I follow, so I keep it systematic here for you. For alkenes, we have already done nomenclature and physical properties and applications and synthesis. We've done a lot of all that, okay? So in the previous chapter where we had substitution and elimination reactions, that's where we covered the nomenclature of alkenes, including, remember, the HDI, the degree of unsaturation, E and Z nomenclature, stability of alkenes. We have done all of that. We talked about physical properties, which were very similar to alkanes, and we learned about applications, which was where they're obtained and where do you use them. So, can go through that. And then synthesis that we did for alkenes was pretty much all elimination reactions, because elimination gives us alkenes. We did primarily two different kinds of elimination, of course, the E1, E2, but the other were depending on the starting material. So we did elimination from alkyl halides and then dehydration of alcohols. Okay, so make sure you go through all of that to learn about what we will call the synthesis of alkenes, which is really elimination reactions, okay? But that's not the only way you make alkenes. As we go on with our study, you will learn more ways to make alkenes, and then we just incorporate all the new synthesis, okay, as we go on. Okay, so for the reactions of alkenes, so first of all, alkenes are unsaturated systems. Unsaturated meaning they can add more things to their compound. And so if you can, then a lot of the reactions are going to be addition reactions. Okay, so remember we talked about classification of reactions way back. And in that one, there were 4 major classes of reactions. We talked about substitution, elimination, rearrangement, and elimination, right? So in any case, so we've done 3 of those reactions already. We've done elimination, substitution, and rearrangement, and now we are on the addition reactions. Okay, so because we are doing reactions of alkenes, so we will go through the mechanisms a lot when we do these reactions. I don't do absolutely all mechanisms, but we will talk about mechanisms for these reactions. Here are all the reactions we are planning to cover for alkenes. So yeah, it's a nice list, okay? But we're not going to do all of them in this presentation, okay? I've kind of distributed it out so that you don't get overwhelmed by all the reactions. The next slide is where we have all the reactions given in reaction manner, okay? So let's look at that. So here is an alkene, okay, an alkene, and then here we can start wherever we want. It doesn't matter because I have, everything in a circle sort of. So hydrohalogenation, where you're adding a hydrogen and a halogen. Then you have halogenation, where you're adding a halogen. Remember, halogen in organic chemistry is X. And then we have hydration, meaning you're adding alcohol group. Okay, hydration also is like adding water, right? So that generally ends up adding an alcohol group. Then halohydrin is where you have the halogen as well as adding OH, okay, or alcohol group. You can also form diols where you have 2 alcohol groups that are added. Then there is another addition reaction, which is carbene reaction. So carbene is an intermediate that we have not seen yet. We've only seen one intermediate so far, and that's been the carbocation. Okay, so we're going to see carbene intermediate in alkenes. Then you can form this kind of a ring, which is called an epoxide. This is an ether. Then there's reduction going on where you completely saturate the double bond. And then this one is oxidative cleavage. And here this is a little bit of a different reaction because look at this, you're actually breaking the double bond. Okay, so all of these are addition reactions, and then this one is the oxidative cleavage, which is a little bit different. Okay, so what I have done for us is I have not covered all the reactions in one PowerPoint, as I said. So in this one, okay, see the pink check mark here, I've covered 4 reactions. Okay, so we will do hydrohalogenation, halogenation, carbene, and reduction here. And then in the next one, there'll be hydration, and in the next one, there'll be oxidative cleavage. Okay, so there are 3 portions, and hopefully that will help you to remember these reactions a little bit easier. So first of all, let's talk about a general mechanism, okay, for these reactions. So the addition reaction that we talk about is actually on the double bond. The double bond is always going to be 2 carbons, right? It's in between 2 carbons, so which means carbon number 1, carbon number 2. So which means when we do the addition is always going to be a 1-2 addition. And remember what I've said about always, okay? So, you know, things sometimes don't always work that way, but right now, the way it's working, it's always like a 1-2 addition, all right? So when you do any kind of a reaction in organic chemistry, so there are, you know, acid-base reaction, oxidation reduction reactions, right? Those kind of reactions. So in this case, what happens is that the alkene is going to be the nucleophile. So which means that you're adding, right? This is addition reaction. So in this addition, it's not really going to be like an oxidation reduction. It's going to be, it can be that also, okay? I mean, if we wanted it to be, but really we're going to talk more about like an acid-base reaction, but not your traditional acid-base. Lewis acid base. Okay, so here is the Lewis base where you have the electrons, and then it's going to react with the Lewis acid, which means an electrophile. Electrophile is the electron poor species. The nucleophile is the electron rich species. So generally all your reactions are going to start like this, where you have the arrow going from the double bond, not from any of the carbons, but from the double bond to the electrophilic center of whatever you're adding in there, and then on one carbon, one of the atoms will attach. You will generate a carbocation. Once that carbocation has been generated, then the rest of the conjugate base will come and attack, and then you end up getting your 1-2 addition. Okay, so the 1-2 addition that's happening is an acid-base reaction going through a carbocation mechanism. Now, the carbocation that you have been aware of so far, we did that in E1 and SN1 reactions. And one of the problems for carbocations is the stability of carbocations, right? So there's the tertiary, primary, secondary, tertiary, and primary is the least stable and tertiary is the most stable. And one of the other problems we encounter with carbocations is that they can rearrange, right? So if you have a primary carbocation, first of all, that's not going to form, right? But you know, even if it does form, it can rearrange. Secondary carbocations can rearrange. Tertiary will not, of course. Okay, that's the most stable one. So keep that in mind as we are going through our mechanisms. I will cover rearrangements again, but I can't cover it all the time, although I think I've given you examples. But you know, I need you to know that as soon as you form a carbocation, that you should look for rearrangement, okay, which means more stable carbocation. So before we get into the reactions, let's understand the different alkene types. And you will encounter these as I'm talking about reactions, okay? So I use these terms all the time. So let's look at the symmetric alkene. Symmetric alkene is when you look at the double bond and you slice it and dice it, then on both sides you will see that you have a carbon and a hydrogen, a carbon and a hydrogen, carbon, hydrogen, right? So they are symmetric. It could be that they are all carbons all around, and that's okay too, or all hydrogens, but it means that it's symmetric when you slice it, okay? And the symmetricity doesn't come from the fact that you have an ethyl group or a methyl group. That doesn't matter. So long you have a carbon, that's what matters, okay? Whether it's methyl or ethyl, it doesn't matter, so long it's carbon, all right? So that means that something is symmetric. Asymmetric is when the double bond has different number of carbons and hydrogens on it. Okay, so if you look at the examples I've given here, on the first double bond I have 3 carbons over here but 1 hydrogen. So these 2 carbons are not the same, right? This carbon has 2 carbons on it. This one has 1 carbon and 1 hydrogen on it. Okay, so similarly this one is different because in both of these 2 carbons they are different. One of the things we've talked about alkenes before is the stability of alkenes. Okay, and so we talked about the fact that, you know, the more substituted an alkene is, the more stable it is. So, you know, all of this is going to play a role in the reactions also, okay? So here, when I talk about symmetric alkene, it means do you have a carbon and a hydrogen, all right, on either side, on each of those carbons. So that's about symmetric and asymmetric. Now, alkenes can also be terminal or internal. Terminal alkenes you will see kind of hanging out there with the CH2. Okay, so here is a carbon with the H2. Whatever number of carbons you have on the other side, it doesn't matter, but it's the alkene itself is out there and it has 2 hydrogens on it. Okay, then you have an internal double bond where the internal can be within a ring. It could be, you know, in a straight chain, whatever it is. So I've just given you a couple examples here where both of these alkenes are internal. Now, here's another way to look at this. This alkene here, the cyclopentene that I have, this is also a symmetric alkene. Okay, because if you slice it, then you have a carbon and a hydrogen and a carbon and a hydrogen, right? So this is symmetric also. This, on the other hand, is not symmetric. So there are, you know, all these different ways of looking at an alkene, which once you start looking at it that way, it really helps you to understand the reactions we are going to learn. So let's start with hydrohalogenation. Hydrohalogenation is when you're adding any kind of a hydrogen attached to any kind of halogen. Okay, so halogen generally for us is of course group number 7, but then you also know when I'm talking about group number 7, we don't really account for fluorine here because fluorine is a little bit different. So when we say halogen, we're generally talking about chlorine, bromine, iodine, even sometimes not iodine. Okay, so a lot of times just chlorine and bromine. So when you add either hydrogen chloride or hydrogen bromide, which is usually added as an acid, so hydrochloric acid or hydrobromic acid, when it's added to an alkyl halide, what happens here? Okay, so this is what I'm talking about, being a symmetric alkene versus an asymmetric alkene. Okay, so here is a symmetric alkene in the sense that you have a carbon and a hydrogen and a carbon and a hydrogen on the other side. Okay, it's symmetric. So now when you add HBr to a symmetric alkene, this is the kind of product you get. Okay, remember this is 1,2, but it can also be the other way, 1,2, right? So we're not really saying which carbon gets the hydrogen. That's not what we are saying over here because both of them have equal amount of hydrogens here. So if both of them have equal amounts of hydrogen, then any of them can get the hydrogen and the other one can get the bromine. Remember, you form a carbocation during the mechanism, which we will write the mechanism in a minute, okay? So this is what you end up getting. So which means you get 2 products over here. And these 2 products are different, right? So this one is 1, 2, 3, 3 bromopentane, and this one is 2 bromopentane. So you're getting 2 products in this case, all right? And not because it's a symmetric alkene, but because you got 2 products because it's asymmetric in the sense that you have a methyl group and an ethyl group, okay, but symmetric in the sense that you have a carbon and a hydrogen and a carbon and a hydrogen, okay, on either of those 2 or both of those 2 carbons. Okay, now let's look at an asymmetric alkene. Asymmetric alkene would be where you have a carbon and a hydrogen over here, and this one then has two hydrogens, okay, on this side. You can call this one terminal alkene also if you want to, okay. So in this case of asymmetric alkene, when you add HCl, okay, then you only get one product, okay, and this is the only product that is formed. What is going on in this product? The hydrogen has gone to the carbon with more hydrogen. Now, if you're wondering where are the hydrogen, remember, invisible hydrogens, right? So there are two hydrogens here and there is one hydrogen here. So this hydrogen actually went to the carbon with more hydrogen, and that's the product you form. That's the only product you form. You don't form this one. So which means in the case of the symmetric alkene, where you end up forming two products, in the case of asymmetric alkene, you only form one product. Okay, so which means that the symmetric alkene has something to do with this. So what does it have to do with it? Let's look at that. So let's see why we got the products we got, okay, which means why is it that we only got one product when you had an asymmetric alkene or a terminal alkene, okay, for that matter. So we have to start looking at the mechanism for this one. So the first step is for the double bond, which remember is the Lewis base, is going for the proton, because HCl is a traditional Bronsted-Lowry acid. Okay, so it's going for the proton over here. So where does the proton go? The proton is going to go to the terminal carbon. Why is it going to go there? Is because you generate a more stable carbocation this way. If this hydrogen is picked up by the internal carbon, then the carbocation you generate is primary, okay, which is not stable. All right, so a secondary carbocation is much more stable. So that's why you end up forming a secondary carbocation. And why did that happen? Is because hydrogen went to the carbon with more hydrogen, and that is Markovnikov's rule, by the way. Okay, so now when the chloride comes and attacks the secondary carbocation that was formed here, you end up getting this kind of an addition, and you will never ever get this kind of an addition. So okay, not never, not through this mechanism. Okay, you will not get it through this mechanism. So this kind of product where hydrogen goes to carbon with more hydrogen, these are called Markovnikov's reactions. So Markovnikov is when you're adding some kind of a hydrogen, you know, anything, whether it's with water or with HCl, the hydrogen goes to the carbon with more hydrogen. So, and now that we know the reason for that is because of the formation of the carbocation. That's why this happens. So when we have carbocation mechanisms, we will have rearrangements, and the rearrangements, if you remember, are for making a more stable carbocations. The only things you can shift are hydrogen, methyl, or phenyl. That's it. And you can do the shift, you know, only from one carbon, and you can't keep shifting again and again, right? So those were the rules we learned back when we learned rearrangement. So let's look at this mechanism here. So here we have a double bond, asymmetric. So in this case, of course, you know, as usual, the hydrogen will go to the carbon with more hydrogen. I didn't draw it out because, you know, we don't want to bother too much, but right there is going to be the hydrogen that we just added. So we create the carbocation right here. So because it's a secondary carbocation and there is a possibility of making it into a more stable carbocation, we can shift this hydrogen to here to the carbocation as I've shown. And again, you don't have to write the hydride shift. You just have to show the arrow, and that's good enough for me. I don't need you to write the H shift. In fact, I encourage you to not write it. I'm just writing it because, you'll have a PowerPoint and you'll wonder what I did here. So in any case, so once you do the hydride shift, then you have a carbocation, which is the tertiary carbocation. Okay, and so then this is what you're going to form. Okay, so you will never form this, by the way, and you will also not form, and I will write this later on, is you will also not form this, okay, at any point, which you would have gotten if you had not done the rearrangement. Okay, so this was the anti-Markovnikov, right? So Markovnikov is when hydrogen adds to the carbon with more hydrogen, and then this one would be without the rearrangement. Okay, so I'll add that on the PowerPoint when I'm doing it. So whenever there is a possibility of rearrangement is going to happen. Okay, you can't avoid it. Okay, and now let's get to halogenation. Halogenation is, of course, adding of a halogen. Halogens are bromine and chlorine. Again, we're not going to consider fluorine and iodine over here, okay? Because when we do halogenations, only those two halogens are used a lot, okay? Again, you're doing a 1,2 addition unless there is going to be rearrangement or something like that, which in this case, there isn't any, okay? But anyhow, so in halogenations, first of all, there is no clear chlorine electrophile or nucleophile because both of these are nonpolar. Okay, so it's really weird how this reaction works. It works beautifully, okay, but still there is no clear electrophile or nucleophile. Okay, the other thing is that these reactions, especially for bromine, this is accompanied by a color change because bromine is red color, and then when it adds, there's no more of that red color. So this is a qualitative test. I have given you qualitative tests wherever there are at the end of the PowerPoint also, okay, because for me, these are important tests for you to have as a separate entity also, because you will see them in the lab and you may see them when we do structure determinations. Okay, all right, so let's look at the addition here. So addition here, this is a double bond, and this is a symmetric double bond, by the way, because you have a carbon and a hydrogen and a carbon and a hydrogen. Okay, nothing to do with the ethyl methyl again. So it's a carbon and a hydrogen thing. So it's a 1,2 addition. That's how it's going to be. So the way this works is that when you add bromine to it, this is the kind of product you get. Okay, so remember here what I've done. This is the stereochemistry. Okay, so I have done this specifically. I didn't write that for the chlorine or the hydrohalogenation, but for halogenation, I'm showing you that one Br is coming out, the other one is going back, and this is called anti-addition. Okay, so which means you're adding things on the opposite side. So how does this happen? How do you add things on opposite side? For that, we have to look at the mechanism. The mechanism is kind of straightforward. Again, there is no clear nucleophile or electrophile, okay, but this is still a nucleophile, and bromine is not really polar, but still the double bond attacks one of the bromines here. You end up forming this kind of a species, which is called the bromonium ion, okay, because bromine is supposed to have only one bond. When it has two, it has the formal charge. Okay, so that's called the bromonium ion, and this is highly stressed out. So the next bromide, the ion that you formed here, the bromide, that comes in, attacks over here, and then relieves this ring, okay, the three-membered ring here. So this attack is happening only from the back side because the front side is obviously too sterically hindered. All right, so you have to attack from the back side. So once it's attacking the back, then you have a bromine in the front and a bromine at the back. Now, which one is going to the front, which one is going to the back, you don't know, so which means you end up forming enantiomers. Okay, so you'll always get a racemic mixture here. So the best way to avoid forming a racemic mixture is to get something that is symmetrical. Okay, so you don't have to worry about separating things out. But this is it. Okay, you will always get an anti-product in this, and this is called an anti-addition. And then we have hydrogenation. Hydrogenation meaning you're adding hydrogen. Again, it's a 1,2 addition. So this reaction actually needs hydrogen. It also needs a heavy metal. You can use palladium, platinum, or nickel. Any of those are used. And the reason for that is because hydrogen is a very light gas. Okay, it's the lightest gas on the periodic table. So it's, just mass of 2. So because it is so light, it just keeps moving so fast, okay? And if you remember the collision theory, the molecules have to collide and also collide in the proper orientation in order for reaction to happen. But if one of the molecules is moving so fast that you can't even catch it, forget about alignment, okay, then we have a problem. No reaction is going to occur. So which means this catalyst here that we have, any heavy metal catalyst, that will hold on to the hydrogen. So this is kind of what I've shown here very crudely, that the blue line here is the heavy metal, which is holding on to the hydrogen. Now, how this is holding on? This is called adsorption. So this is just a surface property. And so once it kind of adsorbs the hydrogen on its surface, now the hydrogen cannot go anywhere. Okay, so which means that and comes an alkene. Now the alkene can align in with the hydrogen and form a bond. Okay, so the dashed lines that you see is the bonds that are forming between the hydrogen and the double bond, which means hydrogen is getting picked up on the same side. If it's getting picked up on the same side, that is called a syn addition. Okay, so anti was opposite and syn is the same. Now this is SYN, not SIN, so it's really not a bad deal. Okay, so but anyhow, so it's a syn addition. You will still get enantiomers. Again, you can avoid that by having symmetrical compounds, but otherwise that's the nature of hydrogenation. Okay, so hydrogenation is a very common thing to do for alkenes. Okay, it is done in the labs quite routinely. It's also done in industry quite routinely. One of the biggest problems for hydrogenation is that hydrogen gas is combustible, so you have to be very careful. A lot of times, if you do small time hydrogenations, you can do them in the lab. But if you have to do big time hydrogenations, you're doing, for many double bonds, or you need a lot of hydrogen, in those cases, you're actually banished from the chemistry department building. You either go on the rooftop or you go out somewhere, in another shed to do the hydrogenation, because it is combustible gas, so you don't want to cause any explosions in your lab. Okay, so small time hydrogenations, sure, you can do that in the lab. Okay, and there are other ways to do it rather than passing hydrogen through your substrate. There are other ways. Just as I said, there is adsorption of hydrogen gas on the metal. You can actually create metal that has hydrogen adsorbed on it. Okay, and so you don't have to have hydrogen gas. So if you're doing, small hydrogenations, you can just use a catalyst with hydrogen on it. Okay, so that works out as well. Anyhow, so that's hydrogenation. Remember, again, you need a catalyst, you need a syn addition over here. And then finally, carbene. Carbene is probably going to be one reaction that you don't really encounter a whole lot, but carbene is a very specific intermediate. Okay, remember, it has a lone pair of electron. It's neither positive nor negative. The reaction also is very specific for carbene that we are doing here, at least. So there are two things that are happening. Okay, first of all is that you have to generate the carbene. Second is the addition to the alkene. Okay, that's what's happening. So here, if you look at this carbene has two hydrogens on it. Okay, then here the carbene we are going to generate has two chlorines on it. That's why you're getting the two H's here and you have the two chlorines here. All right, in each of these cases, when you add a carbene to a double bond, you end up getting cyclopropane, which is a three-membered ring, which, if you remember, we talked about this. It's a highly stressful ring. Okay, and so you have to be very careful. It's a good reaction though. Okay, we do this in the lab all the time and we get good products, so we know it works, and it's really not that hard to do, okay, in the lab. So the reagents that you need for for doing the reaction with carbene is you need the CH2I2, which is diiodomethane with zinc and copper. So those are the catalysts that you need to generate the carbene. Okay, and here the carbene that's generated is by using chloroform and potassium hydroxide. So this is a strong base. It picks up the hydrogen and then picks up another chlorine, and that's how you get the electron pair there. Okay, and then you have the two chlorines added on here. So it's a symmetrical kind of an addition. You cannot get a trans addition. You only get a syn addition. A trans addition would be, if you had the cyclopropane ring where one was coming out, one was going back. I mean, that's a highly stressed out ring, so that's not going to happen. That would be almost like twisted ring. Okay, not the twisted reaction, but twisted ring. Okay, so that's not going to happen. So that's why you have only one kind, and it can either be this or the enantiomer. Okay, so you'll always get the enantiomer wherever you see stereochemistry. But that's it. That's the only reaction we have for carbene here for us, and I think this is also one of the last reactions in this PowerPoint. So we've done only 3-4 reactions. Okay, over here in the next PowerPoint we'll have more reactions. So let's see, that's it. Some of these reaction terms we have learned here already. And then qual tests, again, as I said, they are important. And so we will have that in the last PowerPoint because there are still more, okay, to talk about.